The winter of 1939 settled uneasily across the scientific corridors of America, a nation watching the world collapse into conflict while still clinging to the hope that distance might offer protection. Universities hummed with quiet anxiety as physics departments whispered of breakthroughs emerging from Europe, breakthroughs with terrifying implications. Reports drifted across the Atlantic of German laboratories achieving new insights into nuclear fission, a discovery so profound it threatened to rewrite the nature of warfare itself. American scientists, many of them émigrés who had fled fascist persecution, sensed the urgency long before most policymakers did. They understood that the world was no longer governed by the weapons of the previous war. A new age was forming, an age where physics, chemistry, and engineering could reshape the battlefield in ways no general had ever imagined. Inside the academic sanctuaries that had once served as temples of pure knowledge, the atmosphere shifted from collegial curiosity to a quiet, electrifying race against time. Chalkboards once filled with abstract equations now bore calculations whose potential consequences felt almost mythic in scale. Laboratories smelled of warm circuitry, solvents, and the faint ozone of early electronic experimentation, a sensory backdrop to minds working at the edge of human comprehension. The scientists understood the stakes in a way few civilians could. If Germany harnessed the emerging knowledge of nuclear physics and advanced weapon design before the Allies did, the outcome of any future war would be predetermined. Even those who considered themselves pacifists or idealists faced the same grim realization. Knowledge itself had become a battlefield, and the first side to master these unprecedented powers would hold the fate of nations in its hands. American government officials initially struggled to grasp the scope of what their own scientists were warning them about. The United States, still gripped by isolationist sentiment, had not yet committed itself to the global struggle. Congress debated neutrality, while the laboratories debated chain reactions. As diplomats spoke of treaties and embargoes, a small community of physicists tried to convey that a discovery made months earlier in a German lab, uranium atoms splitting, releasing immense energy, could, if engineered correctly, produce a weapon not just more powerful than existing explosives, but fundamentally different in nature. The gap between these two conversations revealed the danger. Science was moving faster than geopolitics, and the consequences of that mismatch were potentially catastrophic. Within this atmosphere, the personal stories of the scientists themselves became woven into the larger narrative of a world on the brink. Refugees such as Enrico Fermi, Leo Szilard, and many others arrived in America carrying not only their scientific expertise, but also the weight of experience from totalitarian regimes that had dismissed or weaponized their colleagues. Their presence sharpened the sense of urgency within American institutions. These were individuals who understood firsthand how swiftly a nation could mobilize its scientific capabilities toward conquest. Their pleas carried credibility not because of theoretical speculation, but because of lived experience. They warned that Germany's head start in nuclear research was real, and that in the wrong hands, such power could plunge humanity into an era of destruction beyond imagination. Even as these warnings took shape, the scientific community confronted an internal struggle: how to reconcile their devotion to discovery with the moral burden of turning that discovery into instruments of war. Many had chosen careers in academia precisely to avoid the entanglements of military use or political influence. Yet the geopolitical reality left little space for idealism. Those who had once pursued knowledge for its own sake now found themselves sketching designs for devices capable of harnessing physical forces humanity had never controlled. The transformation was swift and emotionally disorienting, as physicists realized that the future of civilization might depend on their willingness to build something they feared might one day overshadow all previous horrors of war. Across the Atlantic, events unfolded that only deepened the scientists' conviction that time was slipping away. Reports of German advances in rocketry, chemical engineering, and advanced metallurgy circulated among American research circles, each new development contributing to a mounting sense of urgency. The Blitzkrieg in Poland, the fall of France, and the rapid spread of Nazi influence across Europe demonstrated the lethal efficiency of a regime that had fused military ambition with scientific innovation. American researchers understood that the laboratories of Berlin, Munich, and Hamburg were not merely academic spaces. They were engines of conquest, foundations upon which Hitler sought to build a new world order enforced by unprecedented tools of destruction. As the year edged toward its midpoint, a quiet fear began to take root among those who understood the science most intimately, the fear that they were already too late. Theoretical papers from German physicists hinted at experiments that suggested their researchers had also grasped the terrifying potential of uranium fission. The notion that Nazi Germany, with its industrial resources and ruthless mobilization, might be racing toward the same goal chilled American scientists. The pace of their own work intensified, not because of official orders, but because of a collective realization that the margin for delay was non-existent. Every day lost to bureaucratic caution or academic hesitation increased the chance that Hitler's regime would cross the threshold first. And yet, amid this tension, the seeds of America's scientific mobilization quietly began to take root. Letters were drafted. Private conversations were held in university offices and government hallways. Committees formed in hushed secrecy, composed of individuals who understood that the future required a new alignment between government, science, and industry. The scientists recognized that the United States possessed one advantage that Germany did not: a vast, decentralized network of brilliant minds, unbound by ideology, capable of collaboration on a scale the world had never seen. But unlocking that potential required the government to listen and to act with unprecedented speed. By the end of this initial period, a subtle shift had taken place across America's scientific landscape. What had started as scattered warnings and isolated discoveries was coalescing into a movement, still tentative, still fragile, but undeniably gathering momentum. The race had begun not with a thunderclap, but with a whisper. The whisper of fission, the murmur of possibility, the quiet dread that something unimaginable was now within reach. America's scientists, driven by fear, hope, and an almost mythic sense of responsibility, were preparing to step into a realm where human knowledge might transform the course of the war and the trajectory of civilization itself. The early months of 1940 brought a new level of intensity to the quiet scientific alarm spreading through America's research institutions. Evidence mounted that German physicists had not only grasped the theoretical implications of nuclear fission, but were actively working to isolate the materials needed to sustain a chain reaction. The Kaiser Wilhelm Institute in Berlin, once a cornerstone of peaceful scientific excellence, now appeared to be reshaping itself into a secret foundry of wartime innovation. American scientists studied every scrap of information they could obtain: conference papers, refugees' testimonies, intercepted academic correspondence, and the more they pieced together, the clearer the picture became. Germany was reorganizing its physics community, redirecting talent into military channels, and securing heavy water supplies from occupied Norway. Each new fragment of intelligence reinforced one chilling conclusion: the window to act was shrinking. This growing certainty created an unprecedented dynamic within American science, as researchers who had once worked in isolation from national security suddenly found themselves thrust into conversations with military strategists. But even with these early warnings, the structure for a coordinated national scientific effort barely existed. Government agencies were not yet accustomed to listening to physicists or chemists when assessing global threats. Funding channels were slow, and interdepartmental rivalries often stifled innovation. Into this bureaucratic inertia stepped a small group of scientists who understood that conventional processes would not be enough. They began quietly building alliances between universities, private research foundations, and sympathetic officials, laying the intellectual groundwork for what would eventually become the largest scientific mobilization in human history. The most pivotal moment in these early organizing efforts came not from Washington, but from the desks of scientists who recognized that only the highest levels of government could be moved to action. In a modest Long Island study, a group of physicists drafted a letter that would become legendary, articulating the danger posed by nuclear research under Nazi control. Though Einstein's signature would give the document historic weight, the technical warnings embedded in its pages reflected the fears of the entire scientific community. The letter described the possibility, still theoretical, still unproven, of a weapon of unimaginable destructive force, one that could annihilate entire cities. It warned that Germany, with its early expertise, might already be moving in that direction. The message was clear: the United States could no longer afford scientific complacency. When this warning finally reached the White House, it landed in an environment still unsure whether America would even enter the war. Franklin Roosevelt, navigating the complex political terrain of neutrality, domestic recovery, and global instability, faced a decision that required him to step into the uncertain world of emerging technologies. Yet the scientist's letter resonated with him in a way few had expected. Roosevelt understood that nations could not wait for wars to define their strategies. They had to anticipate threats before they materialized. He approved the creation of an advisory committee, small, underfunded, and tentative, but it marked the moment the U.S. government formally entered the scientific race. The door had opened. The challenge now was to build something powerful enough to meet the urgency. The creation of this committee, though modest on paper, began to reshape the relationship between American science and government. Physicists who had spent their careers deriving equations in quiet lecture halls found themselves summoned to Washington to explain, in language accessible to policymakers, the nature of chain reactions, neutron capture, and the staggering energy contained within atomic bonds. These meetings were often tense, not because of disagreements, but because the information being discussed stretched beyond the imagination of those hearing it. The notion that a small amount of matter could yield energy equivalent to thousands of tons of TNT strained the mental boundaries of even seasoned military planners. But as the scientists laid out their reasoning, a new understanding took root. The next war would be shaped not just by armies and fleets, but by laboratories. Even as the advisory committee began conducting its preliminary evaluations, the global situation deteriorated. German forces swept across Western Europe with terrifying speed, demonstrating the efficacy of a military doctrine fueled by mechanization, chemistry, and engineering. American observers realized that German science was already influencing the battlefield in profound ways. The V-weapons program was still in its infancy, but early reconnaissance reports hinted at experiments in long-range rocketry and advanced aerodynamics. Chemical weapons, though not yet deployed on the front lines, were being stockpiled in quantities that reflected Hitler's willingness to defy international norms. These developments underscored a painful truth. Scientific innovation was no longer a theoretical advantage. It was reshaping the war in real time. Within American laboratories, this global instability tightened the resolve of scientists who had once questioned whether involvement in military research aligned with their values. The fall of Paris, the Luftwaffe bombings, and the persecution of intellectuals across Europe created a moral reckoning. Many researchers realized that refusing to act would not shield them from responsibility. It would merely leave the world vulnerable to those who saw science not as a tool for progress, but as a weapon of domination. Laboratories that once echoed with the quiet hum of academic debate now buzzed with urgency. Equipment orders surged. Experiments accelerated. The sense of a race, one defined not by speed alone but by the survival of democratic civilization, became impossible to ignore. By the end of this formative period, the United States had begun assembling the fragments of what would soon become a vast scientific machine. Funding slowly increased. New subcommittees formed. Experiments once conducted on shoestring budgets gained access to industrial resources. The government, though still cautious, began to see scientific research not as an abstract intellectual pursuit, but as a strategic asset of national importance. And across the nation, a feeling emerged, subtle, unspoken, yet unmistakable, that the world had entered a new epoch. The tools of the future were taking shape in laboratories from Berkeley to Chicago, and whether they would determine victory or catastrophe depended entirely on who mastered them first. The turning point in America's scientific mobilization arrived as researchers began to confront the immense complexity of transforming theoretical insights into physical reality. It was one thing to calculate the potential of atomic fission on a chalkboard. It was another to produce the materials necessary to sustain it. Theoretical physics had sketched the outlines of a new world, but metallurgy, chemistry, and engineering would have to construct it brick by brick. As scientists began studying the practical requirements for creating a bomb, or even a controlled chain reaction. They were struck by the enormity of the undertaking. The quantities of pure uranium-235 needed were staggering. The separation techniques were unproven. The industrial scale required was unlike anything the United States had ever attempted. Yet instead of discouraging researchers, this challenge ignited a kind of fierce, collective determination. They understood that if they did not attempt the impossible, someone else, someone far more dangerous, would. At the same time, the scientific focus broadened beyond nuclear research alone. American military strategists realized that Germany's rapid development of new technologies was not confined to the atomic realm. Early reports hinted at progress in aerodynamics, guided missiles, high-strength alloys, and forms of electronic warfare that had no counterpart in the American arsenal. Scientists at MIT, Caltech, and numerous smaller institutions began receiving quiet invitations to participate in classified research aimed at closing the technological gap. Radar, still a young and imperfect technology, became one of the first focal points. American radar systems lagged far behind their British counterparts, whose early warning network had proven decisive during the Battle of Britain. Recognizing this gap, American engineers launched a crash program to reinvent radar from the ground up, transforming it from a fragile laboratory curiosity into a robust battlefield tool capable of seeing through darkness, fog, and ocean storms. These developments marked the beginning of a dramatic cultural shift within American scientific life. Research that had once taken place in open academic settings now migrated behind locked doors, guarded gates, and new layers of secrecy. Laboratories adopted practices more reminiscent of espionage than academia. Compartmentalized information, coded documents, classified experiments. Many researchers struggled with the psychological weight of this secrecy, particularly those accustomed to the free exchange of ideas. Yet they adapted, driven by the understanding that the nature of their discoveries demanded such measures. In time, a new kind of scientific culture emerged, one defined not only by intellectual rigor, but also by national responsibility, urgency, and the grim knowledge that their success or failure could alter the course of the war. By 1941, the United States had begun to invest more heavily in the scientific arms race, though still not at the scale the situation required. Research committees expanded, government funds flowed more reliably, and new laboratory facilities appeared at universities across the country. But it was the collaboration between scientists and industry that proved most transformational. American industry possessed capabilities unmatched by any other nation: mass production, advanced machining, and an engineering workforce accustomed to solving difficult problems at industrial scale. When scientific teams began working alongside industrial designers at companies like Westinghouse, General Electric, and Bell Labs, the pace of innovation accelerated dramatically. For the first time, the United States began to see what a fully mobilized scientific-industrial partnership might achieve. Even as these collaborations took shape, the threat from Germany continued to evolve. Allied intelligence intercepted increasingly alarming reports about German progress in rocketry, including tests of engines capable of reaching unprecedented altitudes and velocities. These early signals of what would later become the V-2 program unsettled American strategists, who recognized that long-range missiles could rewrite the rules of warfare. Scientists at Caltech's Jet Propulsion Laboratory, then a small and relatively obscure research group, began quietly studying the fundamentals of rocket propulsion, not yet aware that their work would eventually give rise to an entire field of missile technology. The feeling within these circles was unmistakable. Germany was reaching for weapons that could strike from distances once considered impossible, and the United States could not afford to fall behind. Meanwhile, the atomic research effort continued to expand, drawing in some of the brightest minds from across the nation. New discoveries about neutron behavior, reactor design, and isotope separation methods emerged with astonishing speed. At Columbia University, experimentalists refined gaseous diffusion techniques. At Berkeley, cyclotrons pushed the limits of particle acceleration. At Chicago, theoretical physicists wrestled with the mathematical underpinnings of chain reactions. Yet with each step forward came new revelations about the sheer scale of the undertaking. The scientists understood that they were not merely conducting experiments. They were mapping new territory in the physical world, territory whose dangers and possibilities stretched far beyond their original expectations. Throughout this period, the emotional landscape of American science grew increasingly complex. Many researchers felt a deep tension between the exhilaration of discovery and the dread of what those discoveries might unleash. They were venturing into realms of physics and engineering that no one had ever explored, and with each breakthrough came a haunting awareness that their work could lead to weapons unlike anything the world had seen. Some questioned whether they were crossing moral boundaries. Others reasoned that the true immorality would be allowing tyrants to seize the future unopposed. These internal struggles rarely reached the public eye, but within laboratories they were constant companions, shaping the way scientists viewed their work, their responsibilities, and their place in history. By the time these complex dynamics converged, America stood on the threshold of a transformation that few could yet comprehend. The pieces were being assembled: scientific committees, industrial partners, academic laboratories, government liaisons. But the system that would eventually revolutionize warfare was still incomplete. Yet one thing was now undeniable. The race for unprecedented weapons was no longer a distant or hypothetical concern. It had become a central pillar of America's wartime strategy, driven by minds who understood that the battles of the future would be won not only on fields and seas, but in the deepest corners of physics, engineering, and human ingenuity. As 1941 progressed, American scientific mobilization gained momentum, yet it remained fragmented, an intricate lattice of small committees, university laboratories, industrial workshops, and military oversight bodies. What the nation lacked was a unifying force powerful enough to bind these separate efforts into a cohesive whole. The attack on Pearl Harbor shattered the last illusions of distance and safety, thrusting the United States fully into the war and eliminating the political hesitations that had constrained scientific action. In the days that followed, the government shifted from cautious support to urgent acceleration. Every technological possibility, no matter how experimental, expensive, or improbable, was now considered essential. Scientists across the country found their research abruptly reclassified, their projects expanded, their funding no longer questioned. The war had fused science and national survival into a single imperative. With America now fully mobilized, the scale of scientific ambition expanded dramatically. Radar laboratories at MIT were reorganized into the sprawling Radiation Laboratory, or RadLab, which rapidly became one of the most important scientific institutions of the war. Under its roof, engineers, physicists, and mathematicians worked relentlessly to perfect systems capable of detecting enemy aircraft, submarines, and surface ships at unprecedented distances. They refined magnetron technology, overcame reliability issues in high-frequency circuits, and transformed radar from a fragile prototype into a decisive battlefield advantage. The RadLab's corridors hummed with the constant vibration of vacuum tubes, oscilloscopes, and testing rigs that ran day and night. The researchers understood that each improvement could save thousands of lives, prevent surprise attacks, and blunt the reach of German and Japanese forces. At the same time, American strategists recognized that gaining technological superiority required a deeper understanding of enemy capabilities. Intelligence operations intensified, focusing on German and Japanese research programs. Bletchley Park decrypts, refugee testimonies, smuggled documents, and aerial reconnaissance all contributed to a growing, but incomplete, picture of the Axis scientific effort. The information was often fragmentary, but it hinted at a landscape of innovation. German progress in rocketry, advances in synthetic fuels, and rumored experimentation with new forms of propulsion. These glimpses into enemy laboratories fueled American determination. Each intercepted clue suggested that the Axis powers were reaching for weapons designed to extend their influence, control the skies, and reshape the war's trajectory from afar. For American scientists, the message was unmistakable. Innovation was not optional, it was survival. One of the most pressing problems facing the United States at this stage involved submarine warfare. German U-boats prowled the Atlantic with deadly efficiency, threatening the supply lines that sustained the Allied war effort. American scientists responded with a flurry of innovation, developing new sonar technologies, magnetic anomaly detectors, depth-charge timing systems, and improved hydrophones capable of distinguishing submarines from ocean noise. These developments required meticulous testing in harsh marine environments, often involving long nights aboard research vessels battling rough seas, while operators adjusted experimental instruments by hand. For many scientists, these hands-on experiences blurred the boundary between laboratory and battlefield, reinforcing the knowledge that their discoveries carried immediate and profound consequences. The push for rapid innovation extended far beyond the traditional boundaries of physics and engineering. Chemists became indispensable as the military confronted the need for advanced materials, industrial lubricants, synthetic rubber, and high-performance explosives. The collapse of rubber imports from Southeast Asia triggered a national crisis, prompting American chemists to launch a massive effort to produce synthetic rubber on a scale previously considered impossible. Their success reshaped entire industries, enabling the production of aircraft tires, vehicle components, and military equipment essential to the war effort. These breakthroughs occurred not in secret laboratories, but in bustling industrial plants, where the air smelled of hot polymers, solvents, and industrial machinery, spaces where scientific discovery merged with the grit of manufacturing. Meanwhile, mathematicians found themselves thrust into roles few had anticipated before the war. The emerging field of operations research became a powerful tool for optimizing everything from supply chain logistics to bombing patterns. These analysts used probability theory, game theory, and statistical modeling to solve practical problems that traditional military planning struggled to address. Their calculations determined the most effective methods to deploy convoys, schedule aircraft maintenance, and position radar stations. Often working in windowless rooms illuminated by the bluish glow of early calculating machines, they shaped strategies that would influence every theater of war. These contributions, though less visible to the public, were pivotal in transforming the chaos of global conflict into a system of coordinated, data-driven operations. With each passing month, the United States became more aware that the war's outcome would hinge on maintaining a relentless pace of innovation. Scientists who had entered the conflict with hesitation now found themselves immersed in an environment of creativity, urgency, and unprecedented collaboration. The boundaries between disciplines dissolved. Aerodynamicists consulted with chemists on heat-resistant alloys. Physicists worked with industrial designers to create new manufacturing techniques. Engineers partnered with mathematicians to interpret experimental data. This fusion of talent created a scientific ecosystem unlike anything the world had seen. A dynamic, collaborative force aimed not at incremental progress, but at achieving leaps so bold they bordered on the unimaginable. By the end of this transformative period, it was clear that the United States had crossed a threshold. The nation was no longer merely responding to the scientific advances of its enemies. It was forging its own path into the unknown. Laboratories grew into miniature cities, industrial plants expanded to continental scale, and research programs matured into vast, coordinated networks. The atmosphere was electric, part anticipation, part fear, part exhilaration, as Americans realized they were no longer simply developing new weapons. They were entering realms of science that promised not just to influence the war, but to reshape the future of human power itself. The United States entered 1942 facing a paradox of unprecedented scale. It possessed the world's largest industrial capacity, yet the scientific projects needed to win the war demanded techniques, materials, and facilities that did not yet exist. Transforming theory into production required building entire industries from nothing, and nowhere was this more evident than in the rapidly expanding nuclear program. The early committees that had debated in cramped Washington offices were now replaced by a sprawling organizational structure that required coordination across universities, industrial corporations, military branches, and newly created scientific boards. The scale of secrecy magnified with each passing week. Thousands of workers were hired for tasks they did not understand, unaware that their efforts were contributing to a weapon so powerful it defied the imagination. America was mobilizing not just soldiers and factories, but its intellectual capital. Every professor, chemist, engineer, and technician capable of contributing to breakthroughs that could tilt the balance of the war. In laboratories across the nation, the once theoretical problem of enriching uranium became a towering practical challenge. Scientists debated multiple methods for separating uranium-235, gaseous diffusion, thermal diffusion, electromagnetic separation, and reactor-based plutonium production. Each approach seemed both essential and impossibly difficult. The equipment required was enormous, the technology untested, and the precision required microscopic. Yet the United States chose not to pursue one path. It pursued all of them simultaneously. This decision, unprecedented in scientific history, reflected both urgency and uncertainty. Engineers began designing facilities the size of small towns to house diffusion plants, while experimentalists worked with dangerously unstable compounds under strict secrecy. The acute shortage of materials, nickel for diffusion barriers, copper for massive coils, and specialized alloys for reactor components, forced America to re-engineer its industrial processes from the ground up. While the nuclear program gathered momentum, the aviation research landscape underwent its own revolution. American aircraft lagged behind Germany's fastest fighters and bombers, whose engines benefited from advanced fuel injection systems, stronger alloys, and high-performance turbochargers. To counter this gap, the United States launched an extraordinary collaboration between military engineers and scientific laboratories. Wind tunnels at Langley and MIT ran day and night, investigating wing shapes, control surfaces, propeller efficiency, and fuselage drag. Metallurgists worked to develop alloys that could withstand the extreme temperatures of high-altitude flight. Chemists refined high-octane fuels that allowed American aircraft to operate with greater power and reliability. The resulting innovations contributed to a new generation of planes, each more capable than the last, each designed for speed, maneuverability, and survivability in the expanding aerial war. At the same time, advances in electronics quietly reshaped the battlefield. Early radar systems were bulky and fragile, requiring trained operators and constant calibration. But the demand for portable, ship-mounted, and aircraft-mounted radar pushed engineers into new territory. They miniaturized circuits, strengthened vacuum tubes, and created power supplies capable of functioning under vibration, heat, and cold. Some of the most critical breakthroughs occurred at the RAD lab, where teams developed microwave radar systems that could detect periscopes of submarines, guide aerial bombers through cloud cover, and map terrain at night. These innovations would later transform not only warfare, but also peacetime aviation and meteorology. Yet at the time, they represented the difference between blind flight and tactical vision, between vulnerability and dominance in the air and sea. The growing breadth of scientific programs created acute logistical challenges. Materials that had once been abundant, such as copper, aluminum, tungsten, and specialized steels, now vanished into classified facilities. Military planners struggled to balance the needs of traditional weapons production with the demands of experimental research. Priority committees were formed to allocate scarce resources, often forcing painful decisions. Should copper be diverted to electromagnetic separation coils, or should it be reserved for artillery shell casings? Should high-grade steel go to a new radar platform, or to the construction of aircraft components? These decisions carried strategic consequences that extended across entire theaters of war. The people making them understood that a single misallocation could delay research by months, or cost lives on distant battlefields. Meanwhile, a parallel revolution unfolded in the world of biotechnology and medicine. Combat zones across Europe and the Pacific were not only battlegrounds of bullets and bombs, but breeding grounds for deadly infections. The need for a reliable, mass-produced antibiotic became increasingly urgent. American scientists, working with pharmaceutical companies, launched an effort to scale up penicillin production on a previously unimaginable level. They improved fermentation techniques, engineered new bacterial strains, and redesigned industrial equipment to handle massive biochemical processes. The resulting breakthrough, an abundant supply of penicillin, saved countless lives, reducing infection rates from battlefield wounds and transforming military medicine. It was a reminder that scientific warfare was not solely about creating more destructive weapons, but also about preserving the lives of those fighting. As scientific departments expanded, the human experience within these projects grew more complex. Laboratories became microcosms of wartime urgency, filled with exhaustion, dedication, and quiet heroism. Researchers often worked 16-hour days, driven by the weight of responsibility. Many lived in temporary housing near remote facilities, isolated from their families and forbidden from discussing their work. They wrestled with problems that pushed the boundaries of known science, celebrating small victories in cafeteria conversations or quiet midnight breakthroughs. The emotional strain was immense. They knew that the weapons they were helping to create would reshape the war, and perhaps the world, and that every delay, mistake, or miscalculation carried consequences far beyond the lab walls. By the end of this period, America's scientific mobilization had reached a scale unmatched in human history. Entire cities of research, some hidden, some openly expanding, were now dedicated to technological innovation. The nation had become a vast engine of experimentation, production, and discovery. The line between scientist and soldier blurred as laboratories became as essential to victory as any battlefield. And though no one yet fully understood where the accelerating pace of innovation would lead, there was a shared conviction that the United States was entering a realm of transformative power. Weapons and technologies once confined to imagination were now taking shape in factories, wind tunnels, reactors, and testing fields. The race toward unprecedented destructive capability had become not just a scientific endeavor, but the defining struggle of the modern age. The United States entered the middle stretch of the war fully committed to scientific escalation, but it was now facing challenges of a different magnitude, problems not of theory or vision, but of scale, durability, and speed. Laboratories had produced promising prototypes, yet converting these delicate, experimental devices into rugged battlefield tools required an entirely different kind of genius. Engineers became the critical bridge between theoretical breakthroughs and wartime deployment. For every radar set, rocket engine, or isotope separator designed by physicists, thousands of engineering refinements were needed to ensure reliability under combat conditions. At factories from Ohio to California, engineers experimented with new manufacturing techniques, precision casting, high-tolerance machining, heat treatments, and assembly line calibration procedures to adapt emerging technologies to the unforgiving realities of war. The transition from laboratory models to deployable weapons was not glamorous, but it was essential, and it consumed enormous reserves of skill, creativity, and patience. Aviation research stood at the center of this transformation. American air crews flying in Europe and the Pacific demanded aircraft capable of climbing higher, flying faster, and surviving fierce anti-aircraft fire. The pressure intensified after the Luftwaffe unveiled fighter designs that incorporated swept wings, advanced superchargers, and early forms of jet propulsion. In response, American research centers accelerated their work on high-performance piston engines while quietly pursuing experimental turbojet development. Laboratories at Wright Field and companies like General Electric experimented with centrifugal and axial flow jet engines, testing materials that could survive temperatures no metal had ever endured. These engines failed repeatedly, melting turbine blades, cracking housings, seizing bearings, but each failure added to a growing body of knowledge. The technology was raw, volatile, and unpredictable, yet it represented the threshold of a new age of flight. While aviation leapt forward, the need to counter German rocketry became increasingly urgent. Reports from Europe described mysterious construction sites on the northern coast of France and strange shapes detected by Allied reconnaissance aircraft. Few understood what they were looking at, but the fear that Germany was constructing long-range missiles grew sharper. Scientists at Caltech's Jet Propulsion Laboratory, once preoccupied with small-scale rocket tests, now undertook a more ambitious series of experiments. They studied liquid propellants, nozzle geometries, combustion stability, and guidance systems, often learning through painful trial and error. Misfires, explosions, and destructive engine instabilities were common. But with each test, successful or catastrophic, American rocketry matured. Though far behind Germany in 1943, the United States was developing a scientific foundation that would later reshape global power long after the war ended. Simultaneously, breakthroughs in communications and cryptography altered the strategic landscape. With global operations expanding across Europe, North Africa, and the Pacific, the United States needed secure, reliable means of transmitting orders to ships, aircraft, and ground units. Mathematicians and electrical engineers collaborated to develop encryption systems that could withstand Axis code-breaking efforts. Vacuum tube scramblers, frequency-hopping radios, and secure teleprinter networks emerged, many of them incorporating mathematical concepts that had never been applied to military communication before. These systems dramatically improved coordination across vast distances, ensuring that commanders could direct complex, multi-theater operations without fear of interception. The invisible world of signals, once a niche specialty, became a decisive front in the technological war. But perhaps no area evolved more rapidly than radar. The MIT Radiation Laboratory, now operating at full throttle, produced innovations at a pace that astonished even the military. Microwave radar sets capable of tracking aircraft at long distances were soon adapted for naval use, giving American fleets a powerful tool against Japanese air attacks. Airborne radar units allowed bombers to navigate through clouds and darkness, reducing losses and increasing accuracy. Surface search radars gave destroyers and escort carriers the ability to detect submarines operating at periscope depth. Each new radar system required extensive field testing, often conducted in harsh environments, from rain-soaked Pacific decks to frozen airfields in the Aleutian Islands. The RAD Lab's work reshaped nearly every aspect of Allied strategy, proving that technological vision, once realized, could become a weapon of unparalleled influence. Yet for all these advancements, America's scientific expansion was not without internal tension. The secrecy surrounding major programs created what some researchers described as islands of knowledge, clusters of brilliant minds working intensely, but often unaware of parallel efforts occurring elsewhere. Scientists sometimes struggled with isolation, unable to discuss frustrations or breakthroughs even with colleagues in the next building. Administrators wrestled with the challenge of coordinating thousands of classified projects while maintaining strict compartmentalization. Miscommunications, duplication of effort, and bureaucratic obstacles occasionally slowed progress. Still, the underlying momentum was unstoppable. The shared sense of mission, the knowledge that their discoveries would determine whether democracy survived, kept morale high even in moments of exhaustion or doubt. On the production lines, the human stories behind scientific warfare unfolded in quieter, but equally significant ways. Skilled machinists learned to craft components with tolerances so tight they had once been considered impossible. Women entering the industrial workforce mastered precision assembly of radio circuits, optical devices, and aircraft instruments. Factory workers adapted to new materials, synthetic polymers, exotic alloys, high-purity metals, whose behavior was poorly understood but essential to emerging technologies. Many workers never learned what their components were used for. They simply followed blueprints with unwavering accuracy, unaware that their hands were shaping machines that would chart the future of warfare. By the end of this transformative period, the United States was no longer simply responding to Axis technological threats. It was beginning to outpace them. The convergence of science, industry, and military planning created a momentum that stretched from university basements to massive industrial complexes. America had become a nation where ideas could be converted into machines at unprecedented speed, and where the boundaries of possibility expanded with each new breakthrough. The weapons being developed, radar-guided bombs, jet aircraft prototypes, cryptographic systems, rocket engines, and atomic devices, were no longer merely responses to enemy innovations. They were the early signs of a technological future that would reshape the world far beyond the war's end. The summer of 1943 unfolded with a sense of volatile transition inside the laboratories of the American weapons programs, a period when theoretical boundaries that had endured for decades began to collapse under the force of relentless experimentation. At Los Alamos, the shift from broad conceptual planning to hands-on engineering introduced a new level of urgency, and with it came an atmosphere that oscillated between exhaustion and exhilaration. Scientists who had once worked primarily on paper now confronted the physical realities of shaping atomic cores, designing firing systems, and determining how to control reactions that no human being had ever witnessed. Every day brought fresh complexities. Metallurgists struggled to understand the temperamental properties of plutonium, which behaved unlike any metal previously studied, often cracking or warping without clear explanation. Implosion specialists pushed their analytic techniques to the breaking point as they attempted to model shockwave behavior in spherical geometries that defied classical intuition. Theoretical confidence was no guarantee of practical success, and the lab began to feel like a place where the laws of nature were being renegotiated one failed experiment at a time. Far from New Mexico, other teams across the United States confronted similarly unprecedented hurdles while advancing weapons technologies intended to redefine naval and aerial warfare. At the Naval Research Laboratory, radar engineers raced to fine-tune microwave detection systems capable of piercing storm clouds, countering German U-boat stealth tactics, and guiding nighttime bombing raids with a precision earlier commanders would have considered impossible. Radar, still a young technology, required enormous leaps in miniaturization, frequency stability, and antenna design. Engineers packed cramped benches with wires, oscillators, and glass vacuum tubes that glowed like miniature furnaces, often overheating under the strain. Every incremental improvement, an extra mile of range, a slight reduction in interference, translated into tactical advantages measured not in abstractions, but in the number of Allied sailors and airmen who might live to see another sunrise. The scientists understood this reality with sharp clarity, and it drove them through sleepless nights where failure never felt theoretical but intimately human. At the same time, aviation research accelerated beyond anything the pre-war world had imagined. The wind tunnels at Langley and Wright Field churned day and night as aerodynamicists sought to unlock the physics of high-speed flight. American engineers, having studied the wreckage of downed enemy aircraft and intercepted intelligence on German experimental jets, recognized that conventional piston engine planes were approaching their physical limits. Compressibility effects, once obscure footnotes in aerodynamics textbooks, had become life-threatening realities for pilots whose aircraft shook violently when approaching the speed of sound. To overcome these barriers, research teams built experimental airframes with razor-thin wings, new fuselage contours, and control surfaces designed to maintain stability in regimes where airflow behaved more like shock waves than smooth currents. This was not just aircraft development. It was the beginning of a conceptual revolution, the first chapter in humanity's transition from traditional aviation to a new era of jet propulsion, guided missiles, and high-altitude reconnaissance. Meanwhile, chemists and materials scientists launched their own parallel race against time, one centered on the development of high-performance explosives and innovative delivery systems. The American military required compounds that were lighter, more stable, and more energetic than anything previously used in combat. RDX, first discovered before the war, underwent massive industrial expansion as U.S. chemists refined production techniques that transformed a once dangerous laboratory curiosity into one of the most widely deployed explosives of the conflict. The creation of Composition B, a blend of RDX and TNT, reflected an extraordinary marriage of chemistry and wartime necessity, enabling ordnance that could shatter reinforced U-boat pins or punch through the thick concrete of Japanese island fortifications. Behind every bomb casing lay thousands of hours of analytical chemistry, refining synthesis pathways, eliminating impurities, and mastering the kinetics that determined whether a weapon detonated with controlled precision or catastrophic inconsistency. Even more secretive work unfolded within the biological warfare laboratories, including Unit 731 intelligence integration and Fort Detrick's expansion into a central node of defensive research. Although the United States pursued biological weapons cautiously and with strict ethical constraints compared to Axis programs, the scientific effort was nonetheless sweeping in scope. Specialists studied the stability of pathogens under varied environmental conditions, examined defensive countermeasures, and analyzed aerosolization mechanisms that could either spread disease or halt it. For many researchers, this line of work carried an unsettling moral weight. Unlike tanks and planes, these technologies blurred the boundaries between military necessity and humanitarian crisis. Yet the brutal realities of Axis experimentation and the fear of an unprecedented biological assault compelled the United States to prepare through science rather than ideology. This was the darker side of wartime innovation, where the race to outthink the enemy intersected with a profound reckoning about the ethical limits of scientific power. Back at Los Alamos, the relationship between theoretical physics and industrial-scale engineering grew more strained as the stakes escalated. The implosion method, now recognized as essential for utilizing plutonium, had forced the weapons program into a labyrinth of challenges involving shockwave symmetry, high-speed detonators, and the physics of compressive hydrodynamics. Physicists like Seth Neumeier and mathematicians under John von Neumann struggled to translate equations into workable designs, often confronting results that contradicted even their best calculations. Every misalignment of the explosive lenses, every distortion in the test assemblies, introduced the possibility that the final weapon would fizzle rather than ignite a sustained chain reaction. The tension surrounding this effort became palpable. The laboratory's success or failure hinged on mastery of phenomena for which no experimental precedent existed. The scientific frontier had become inseparable from the military deadline looming just beyond the horizon. At the same moment, American intelligence units began compiling intercepted German communications hinting at advanced weapons projects, jet aircraft, guided bombs, and the rumored V-2 rocket that U.S. analysts initially struggled to believe was real. These fragments, delivered through secret channels and code-breaking operations, did not merely inform strategy. They electrified the scientific effort with a sense of rivalry that transcended national borders. Suddenly, the American scientific community saw itself not merely as an isolated team of researchers, but as participants in a titanic duel between two radically different visions of technological progress. If Germany mastered revolutionary weapons first, the balance of power could shift so dramatically that entire war plans might collapse. By mid-1944, America's scientific mobilization had reached a point where scale, secrecy, and urgency converged into a singular, almost palpable intensity. Los Alamos had grown from a remote desert outpost into a sprawling complex buzzing with engineers, chemists, physicists, and technicians. Each building contained specialized workshops, from explosive lens fabrication to high-precision machining of tamper and initiator components. The implosion method, long considered a theoretical curiosity, now demanded meticulous calibration and synchronization of hundreds of detonators, a process as exacting as any orchestration of a symphony. Failures were catastrophic and immediate, leaving lessons written in shattered components and scorched concrete. Yet the team pressed on, driven by the unspoken understanding that delay could cost lives thousands of miles away, and that success might end the war faster, saving even more. Across the United States, radar laboratories had transformed into nerve centers for both innovation and training. Airborne units that had once struggled with limited range or unreliable detection now received systems capable of guiding entire bombing formations through dense cloud cover and darkness. Operators trained with mock combat simulations, testing new frequency bands, pulse modulation techniques, and counterjamming protocols. The knowledge that each incremental improvement could reduce bomber losses or prevent Allied ships from being sunk infused every calculation with urgency. Engineers worked alongside pilots and gunners to interpret data in real time, ensuring that theory could be translated into operational effectiveness. The pace was exhausting, but the clarity of purpose was undeniable. These machines were now as critical to victory as any fleet or regiment. Simultaneously, American missile and rocket programs began bridging the gap between concept and feasible deployment. Early prototypes tested at desert ranges and remote research sites were fragile and often failed catastrophically. Combustion instabilities caused engines to explode, guidance fins malfunctioned, and fuel mixtures sometimes reacted unpredictably. Yet each failure contributed critical knowledge. Researchers meticulously recorded every parameter, studied the aerodynamics of every fragment, and iteratively adjusted designs. By 1944, these programs were starting to achieve sustained thrust, stable trajectories, and incremental accuracy improvements. Though far from operational status, they represented a technological frontier that would profoundly influence post-war military strategy and lay the foundation for the space race. Meanwhile, the atomic program's industrial component had expanded to staggering proportions. Oak Ridge, Tennessee, had become a city devoted entirely to uranium enrichment, its facilities humming with the relentless rhythm of diffusion plants, electromagnetic separators, and chemical processing operations. Thousands of workers, most unaware of the ultimate purpose of their labor, operated machinery that would never exist in peacetime. Supervisors managed processes with a rigor born of necessity, understanding that contamination, misalignment, or mechanical failure could halt production for months. The labor force was diverse: men and women, trained technicians and unskilled operators, all integrated into a highly compartmentalized system that depended on trust, precision, and discipline. The scale of effort, the secrecy, and the stakes made the production sites microcosms of a nation mobilized for scientific combat. In the skies over Europe and the Pacific, improved aircraft, radar, and electronic warfare systems were beginning to yield tangible battlefield advantages. Night raids that had once been perilous now had a higher probability of success, thanks to airborne radar units guiding formations safely over enemy territory. Escort fighters equipped with new high-altitude engines could intercept enemy bombers before they reached critical targets. Anti-submarine patrols, enhanced by microwave detection and sonar integration, reduced shipping losses, ensuring supply lines remained intact. Each technological improvement not only saved lives, but also contributed to a psychological edge, instilling confidence in Allied forces while undermining the morale of the Axis. The battlefield had become a laboratory, and every mission an experiment in the application of scientific innovation. The moral weight of these technological advancements grew heavier within Los Alamos and other nuclear research sites. Scientists fully grasped that the weapon they were assembling could annihilate entire cities in a single instant. Philosophical debates about the ethics of mass destruction became more urgent as they wrestled with questions that blurred lines between necessity and morality. The war demanded action, yet every experiment reminded them of the unprecedented human cost of success. These internal struggles were rarely documented outside private journals or whispered conversations in isolated hallways, yet they influenced decision-making, safety protocols, and the careful orchestration of testing. The psychological burden, though invisible, was as real as any mechanical challenge. Industrial collaboration reached new heights, connecting universities, private corporations, and government agencies into a cohesive network. Engineers in one state designed components whose tolerances would only be verified thousands of miles away. Machinists in another produced parts critical for experiments half a continent distant. The national scientific effort became a living organism, its neurons firing across rail lines, laboratories, and assembly plants. Coordination, secrecy, and trust were vital. A single miscommunication could jeopardize a project's success or expose critical information to prying eyes. This massive, distributed collaboration marked an unprecedented feat of organizational engineering, rivaling the scale and complexity of any military operation in history. By the close of 1944, it was evident that America's scientists had not merely caught up with enemy technological programs. They were beginning to define the frontier of modern warfare. The fusion of physics, engineering, industrial capacity, and human determination had created an ecosystem capable of producing weapons that no generation had ever imagined. Atomic devices, high-performance aircraft, advanced radar systems, and nascent missile technology converged to form a matrix of unprecedented destructive potential. The implications were staggering. Not only could these innovations win battles, but they had the capacity to alter the very fabric of international power and the ethics of war. America had become the first nation to harness science at a continental scale, and the world was about to witness the results of this extraordinary convergence. By early 1945, the culmination of years of frenetic innovation had begun to yield weapons of unprecedented power. Los Alamos, once a remote desert laboratory, had transformed into a complex of production, testing, and theoretical calculation, its scientists now operating at the very limits of human ingenuity. Implosion assemblies, precision-engineered explosive lenses, and neutron initiators were refined to levels that had once seemed impossible. Every component was tested meticulously, failures recorded and analyzed, and designs iterated with a rigor that mirrored no previous industrial process. The staff operated under relentless pressure, knowing that mistakes could cost lives, delay the war's end, or compromise the entire project. Yet there was also an undercurrent of exhilaration. They were participating in a scientific endeavor that would permanently redefine human capability. At Oak Ridge and Hanford, industrial-scale production of fissile materials approached completion. The gaseous diffusion plants at Oak Ridge hummed continuously, purifying uranium-235 with a precision that defied imagination, while Hanford's graphite reactors generated plutonium at rates previously thought unattainable. Thousands of workers labored in silence, often unaware of the ultimate purpose of their contributions, yet each task, whether monitoring cooling systems, maintaining pumps, or recording chemical separations, was critical to the final weapon. The scale of coordination, secrecy, and technical complexity was staggering, and managers relied on precise scheduling, compartmentalization, and redundancy to maintain steady progress. It was an industrial ballet of a type never before attempted, producing materials whose destructive potential dwarfed the combined arsenals of previous generations. Meanwhile, American radar and electronic warfare capabilities had matured into strategic assets that reshaped combat across Europe and the Pacific. Airborne radar systems allowed bombers to navigate through storms, evade enemy fighters, and strike with unprecedented accuracy. Shipborne radar guided fleets safely through treacherous waters, detecting submarines, mines, and surface raiders long before human eyes could. Engineers developed countermeasures to jam enemy radar, introducing a subtle and invisible war in the electromagnetic spectrum. Every improvement was tested relentlessly, refined in both laboratories and combat theaters, and applied immediately. Radar, once a fragile experimental technology, had become the eyes and ears of the American war machine, amplifying human perception across continents. Aeronautical research achieved similarly remarkable feats. Experimental engines and jet prototypes, initially fragile and temperamental, reached operational levels suitable for frontline deployment. Piston engine aircraft had been optimized to the limits of material science, while jet engines promised speeds and altitudes previously unattainable. Aerodynamicists had solved problems of compressibility and shockwave management, while metallurgists had devised alloys that could survive extreme temperatures. Every airframe, engine, and instrument was the product of collaboration between theorists, machinists, chemists, and pilots, an interdisciplinary effort that transcended traditional laboratory boundaries. The rapid iteration of prototypes and operational feedback transformed the skies into a proving ground where American scientific ingenuity gained decisive leverage. Rocket and missile research, though still emerging, provided a glimpse into the future of warfare. Experiments with liquid-fueled propulsion, guidance stabilization, and aerodynamic shaping revealed both the promise and peril of these technologies. Desert testing ranges echoed with the sound of misfires, exploding engines, and failed trajectories, yet each failure yielded critical data. Engineers studied turbulence, combustion instability, and structural integrity with painstaking care. Even as the V-2 rocket terrorized European cities, American scientists gained confidence that with persistent innovation, guided weapons could be harnessed for strategic purposes. The psychological impact of this research, on both scientists and military planners, reinforced the sense that the war was as much a contest of technological foresight as of armies and fleets. The human dimension of this accelerated scientific war effort was profound. Long hours, moral dilemmas, and the relentless weight of responsibility shaped the experience of those involved. Many scientists wrestled with ethical uncertainty. The destructive power they were unleashing was unprecedented, and the consequences were almost unimaginable. Private letters, journals, and whispered conversations reveal a mixture of fear, pride, exhaustion, and awe. The emotional landscape of Los Alamos, Oak Ridge, and the Rad Lab reflected the tension of a world simultaneously driven by discovery and terrified of its own creations. Yet the unifying force was purpose. Each person understood that their contribution might shorten the war, save lives, or secure the future of democratic nations under siege. Integration of scientific innovation into military strategy reached unprecedented sophistication. Radar data informed bombing campaigns, guiding squadrons through treacherous weather to key industrial targets. Aircraft improvements allowed new missions at higher altitudes with enhanced survivability. Missile research began informing counter-strategy, even before operational systems existed. The atomic program, still concealed in secrecy, represented the ultimate strategic lever, capable of ending the conflict in ways conventional forces could not. By mid-1945, military planning and scientific development were inseparable, creating a dynamic in which innovation directly determined tactical and strategic possibilities. The battlefield had become a laboratory, and the laboratory had become a battlefield. By the spring of 1945, the United States had achieved a level of technological preeminence never before witnessed in human history. Atomic devices, advanced aircraft, radar-guided operations, high-performance engines, and early guided missiles converged into a formidable arsenal. The war was no longer waged solely with soldiers and ships. It was waged with ideas, experiments, and the disciplined application of science at a national scale. The scientists, engineers, and industrial workers behind these achievements had collectively rewritten the rules of warfare. Their work, fueled by urgency, ingenuity, and a profound understanding of stakes beyond imagination, would leave a legacy that extended far beyond victory, shaping both the outcome of World War II and the trajectory of global power for decades to come. The summer of 1945 marked the final, frantic phase of America's scientific mobilization, as laboratories, factories, and test sites operated at peak intensity in preparation for the ultimate demonstration of the weapons they had been building for years. At Los Alamos, the assembly teams worked under unprecedented pressure, carefully aligning explosive lenses, measuring tolerances to fractions of a millimeter, and verifying the complex timing mechanisms that would trigger a nuclear chain reaction. Every adjustment, every minor calibration, was treated as both a technical challenge and a moral responsibility. Scientists understood that their work represented the culmination of a massive, multi-year effort and that the consequences, once unleashed, would reverberate across the entire globe. The tension in the air was palpable, a mixture of anticipation, fear, and almost reverential awe at the power they were about to release. Meanwhile, Oak Ridge and Hanford continued producing fissile materials at rates that dwarfed all expectations. Uranium-235 and plutonium, once abstract elements in a laboratory notebook, now existed in industrial quantities sufficient to create explosive devices capable of leveling entire cities. Every stage of production was monitored with obsessive care. Cooling systems, chemical separations, enrichment cycles, and storage protocols had to be flawless. The workers, many of whom were unaware of the ultimate purpose of their labor, became part of a vast, compartmentalized machine whose collective output was shaping the course of history. The scale of this operation, coupled with its absolute secrecy, was unprecedented, and the successful integration of theory, engineering, and industrial logistics represented a triumph of human coordination and ingenuity. Across the Atlantic, American radar and electronic warfare teams had fully integrated their technologies into operational theaters. Night bombing missions, once fraught with catastrophic risk, now relied on radar navigation to reach targets with surgical precision. Anti-submarine warfare, guided by microwave detection and sonar, dramatically reduced losses in convoys critical to sustaining the Allied advance. Communications networks, enhanced with cryptography and early encryption systems, allowed commanders to synchronize operations across continents in ways previously impossible. The invisible war in the electromagnetic spectrum had matured into a decisive advantage, demonstrating how innovation, when applied systematically and relentlessly, could tip the balance of global conflict. Aircraft research had reached new heights, both literally and metaphorically. Propeller-driven planes had been optimized to the limit of piston engine performance, while experimental jet and rocket engines promised a transformation in the dynamics of air warfare. Wind tunnel tests, computational aerodynamics, and high-altitude flights combined to produce airframes capable of speeds, agility, and endurance far beyond the experience of most pilots. Engineers collaborated closely with frontline crews to refine designs based on real-world feedback, creating an iterative cycle that married theory and practice. In the air over Europe and the Pacific, these innovations were beginning to manifest as tangible advantages, reshaping strategy and redefining what was possible in combat. Rocketry programs, though still nascent compared to the atomic project, achieved operational milestones that captured the imagination of scientists and military planners alike. Tests of liquid-fueled engines demonstrated stability and controlled flight durations, while guidance experiments offered hope for delivering ordnance with unprecedented precision. The knowledge gained from each failed test, engine explosions, structural failures, and trajectory deviations, was meticulously recorded and used to refine designs. The specter of German V-2 rockets remained a powerful motivator, pushing American teams to explore solutions that would later influence missile programs and even space exploration. The race was no longer theoretical. It was the immediate application of science to secure strategic dominance. Within Los Alamos, the human dimension of this unprecedented project became increasingly intense. Scientists worked around the clock, many under severe stress and isolation, fully aware of the magnitude of their responsibility. Ethical questions lingered in private moments. The consequences of their work would extend far beyond the war, shaping future conflicts and global politics. Yet despite the psychological burden, the collective purpose of the team created cohesion. Researchers, engineers, and assembly crews shared a quiet understanding that their efforts might end the war, save lives in the long term, and establish a new paradigm for scientific capability. This blend of intellectual rigor and emotional weight gave the project a unique intensity, unmatched in any previous human endeavor. Industrial coordination reached near-perfect integration by mid-1945. Components manufactured in factories across multiple states were transported under tight security to assembly sites. Engineers and supervisors tracked every bolt, tube, and circuit with meticulous attention. Laboratories, production plants, and testing ranges functioned as a vast, interdependent organism, each part critical to the survival and effectiveness of the whole. Redundancies were built into every system, not only to ensure reliability, but also to safeguard the secrecy and security of the operations. The scale and precision of this logistical achievement rivaled the most complex military campaigns in history, demonstrating that scientific innovation at a continental scale could be orchestrated with extraordinary efficiency. By the summer of 1945, the United States had effectively transformed the nature of warfare through its scientific and technological mobilization. Radar, advanced aircraft, jet propulsion, missile technology, chemical engineering, and nuclear research had converged into a comprehensive system of unprecedented power. Scientists and engineers, once operating in isolated academic or industrial contexts, had become integral participants in a global struggle, translating abstract theory into tangible, world-altering tools. The work completed over these years demonstrated not only the ingenuity and perseverance of American science, but also the profound and sobering reality that human intellect, when harnessed at scale and urgency, could redefine both victory and destruction in a way no one had ever seen before. The final months of 1945 saw America's scientific apparatus functioning as a single, vast, disciplined organism, where laboratories, factories, and test sites were coordinated with the precision of a symphony. In Los Alamos, the assembly of atomic devices reached its culmination as physicists, engineers, and technicians meticulously aligned detonators, explosive lenses, and initiators. Every test, measurement, and inspection carried extraordinary significance. A single miscalculation could render months of effort useless or endanger the lives of those in future operational theaters. The desert laboratory, isolated from the world, pulsed with an almost sacred intensity, a place where intellect, tension, and moral reflection intertwined. The staff had grown accustomed to working under extreme pressure, yet each day brought new technical challenges and the psychological weight of wielding unprecedented destructive power. Meanwhile, Oak Ridge and Hanford operated as industrial marvels, producing fissile materials at scales that once would have been deemed impossible. Uranium-235 and plutonium, the elements that would make atomic detonations possible, were extracted, refined, and carefully transported under strict security protocols. Thousands of workers, many completely unaware of the ultimate purpose of their labor, performed tasks critical to the success of the atomic project, from monitoring chemical separations to maintaining reactor flows. Each stage required exacting precision, from the timing of enrichment cycles to the handling of highly radioactive materials. The sheer scale of operations, combined with the secrecy and coordination required, demonstrated that modern warfare had become a fusion of intellectual endeavor and industrial capability unlike anything the world had seen. In parallel, radar and electronic warfare technologies had matured into decisive instruments of strategy. Airborne radar systems allowed bombers to navigate through storms, clouds, and darkness with unprecedented accuracy, while shipborne radar ensured that Allied fleets could detect submarines, mines, and enemy vessels well beyond visual range. Advanced countermeasures disrupted enemy detection, creating a subtle but effective layer of technological advantage. Engineers and scientists worked tirelessly to refine systems in the field, integrating feedback from pilots, sailors, and soldiers into new designs. These invisible weapons of perception reshaped the battlefield, demonstrating that intellectual innovation could achieve outcomes as decisive as any conventional force. Aircraft technology had also reached a new plateau. Propeller-driven planes had been optimized to the limits of materials science, while jet and rocket propulsion experiments offered a glimpse into a new era of high-speed, high-altitude flight. Engineers solved aerodynamic problems once considered insurmountable, using wind tunnels, computational models, and flight tests to refine designs. Metallurgists developed alloys capable of withstanding extreme heat and stress. Pilots, engineers, and technicians worked together in iterative cycles, ensuring that theoretical innovations could withstand the brutal conditions of war. These advancements not only enhanced combat effectiveness, but laid the groundwork for post-war aviation, heralding a future of supersonic travel and aerospace exploration. Rocketry, still experimental, began to demonstrate operational potential. Desert tests, often destructive and chaotic, provided critical insights into combustion stability, aerodynamic control, and guidance precision. Engineers analyzed every failed flight, meticulously refining engine performance, structural integrity, and fuel mixtures. Observing the devastating effects of German V-2 rockets in Europe heightened the urgency of the work. American scientists recognized that the mastery of guided, long-range weapons could redefine the nature of conflict. The lessons learned from these early programs would later propel not only military rocketry, but the nascent space programs, illustrating how wartime innovation could echo far beyond the battlefield. The moral and psychological dimensions of these scientific projects became increasingly profound. Scientists grappled with the knowledge that their work could destroy entire cities, ending thousands of lives instantly. Letters, journals, and private conversations reveal a mixture of pride, fear, and profound reflection. Many acknowledged the ethical complexity of their task, questioning how such power could ever be used responsibly. Yet there remained a shared understanding of the wartime imperative. These technologies might bring a quicker end to the conflict, potentially saving lives in the aggregate. The interplay of human emotion, responsibility, and technical achievement created a unique environment where intellect and conscience collided in stark relief. Industrial and logistical coordination reached its apex. Factories across the country produced components with exacting tolerances, which were then transported under tight security to assembly and testing sites. Laboratories, workshops, and field ranges functioned in perfect synchrony, each element supporting the others in an intricate choreography. Redundancies, safety protocols, and compartmentalization ensured that no single failure could derail the entire operation. This integration of industrial engineering, scientific research, and military strategy exemplified the unprecedented scale and ambition of America's wartime innovation, demonstrating that national-scale scientific mobilization could achieve outcomes once thought impossible. By the close of 1945, the United States had fundamentally transformed the landscape of warfare. The convergence of nuclear research, radar, advanced aircraft, jet propulsion, chemical engineering, and early guided missile development created an arsenal of unprecedented destructive and strategic potential. Scientists, engineers, and industrial workers had collectively rewritten the rules of military engagement, demonstrating that intellectual achievement at continental scale could rival the impact of traditional military force. These efforts not only contributed directly to victory in World War II, but also established a technological and ethical framework that would shape global power dynamics, military strategy, and scientific exploration for decades to come. The race to build weapons the world had never seen had succeeded, and the world would never be the same. The end of 1945 marked not just the conclusion of wartime development, but the beginning of a profound reckoning with the consequences of the unprecedented scientific feats achieved in the preceding years. In Los Alamos, the desert laboratories, once alive with relentless experimentation and urgent improvisation, fell into a quieter, more reflective rhythm. Scientists walked among the buildings where they had pushed the limits of physics, chemistry, and engineering, contemplating the reality of what they had created. Every component of the atomic devices, perfectly timed detonators, implosion lenses, and initiators, was a testament to human ingenuity, yet each also embodied a force that could obliterate cities. The interplay between triumph and terror, innovation and destruction, permeated the air, leaving an indelible mark on those who had shaped the project. Across Oak Ridge and Hanford, the enormous industrial complexes that had produced fissile material on a previously unimaginable scale now stood as monuments to precision, organization, and secrecy. Thousands of workers continued their duties, often unaware of the ultimate implications of their labor, yet the efficiency, scale, and discipline of their production remained staggering. Every enriched uranium cylinder and every separated plutonium batch was a testament to a vast, integrated system of science and logistics. The meticulous coordination between laboratories, factories, and testing ranges had produced materials whose potential exceeded anything humankind had ever wielded. This industrial achievement alone represented a leap in human capacity, demonstrating that national scientific mobilization could produce results on a scale previously inconceivable. Radar and electronic warfare continued to demonstrate their strategic significance, having matured into technologies capable of shaping entire campaigns. Bombers equipped with advanced navigation and targeting systems flew with a precision that reduced losses and increased operational effectiveness. Fleets equipped with sophisticated detection systems could anticipate submarine threats and counterattack before losses mounted. The invisible battles in the electromagnetic spectrum had become decisive, showcasing a shift in warfare from brute force to intellectual mastery of technological domains. These developments not only aided in the immediate military struggle, but also redefined the principles of command, control, and communication for modern conflicts. Aeronautics, pushed to the limits by wartime necessity, had achieved remarkable advances. Propeller-driven aircraft reached operational ceilings previously considered unattainable, while experimental jets and rockets foreshadowed a post-war future of supersonic flight and high-altitude reconnaissance. Engineers had overcome aerodynamic challenges, mastered new materials, and integrated feedback from combat pilots into iterative design improvements. These innovations, developed under extreme time pressure and resource constraints, exemplified how necessity can accelerate human ingenuity. The lessons learned in these experimental hangars would inform not only military aviation, but also civilian aerospace development for decades. Rocketry and missile programs, still in their infancy, now hinted at the coming era of guided warfare and space exploration. Tests that once seemed prone to catastrophic failure began achieving controlled trajectories, sustained propulsion, and incremental accuracy improvements. The specter of German V-2 rockets had provided the initial impetus, yet American programs quickly moved beyond imitation, exploring innovations in guidance, stabilization, and propulsion that would define the next generation of strategic weaponry. Each successful test validated years of experimentation and failure, demonstrating the ability of science to transform concepts that once seemed impossible into operational possibilities. The moral dimension of these projects remained ever-present. Scientists, engineers, and administrators grappled privately with the consequences of their innovations, recognizing that they had unleashed forces of destruction previously unimaginable. Letters, memoirs, and private discussions reveal a mixture of pride, anxiety, and ethical reflection. The atomic bomb, in particular, represented both a decisive tool to end the war and a profound challenge to humanity's sense of responsibility. While immediate objectives had been achieved, the broader implications for future conflict, civilian safety, and international ethics weighed heavily on the minds of those who had devoted themselves to these projects. Industrial and organizational achievement reached a historical peak during this period. Factories, laboratories, and field sites had been synchronized with astonishing efficiency, producing components, data, and materials essential to the ultimate success of the scientific effort. The integration of diverse disciplines, physics, chemistry, engineering, mathematics, and industrial management, demonstrated that human collaboration at scale could achieve transformative results. The lessons of coordination, compartmentalization, and precision set a precedent for post-war scientific endeavors, from aerospace engineering to nuclear energy, and illustrated the potential of national-scale projects in shaping both military and civilian futures. By the close of 1945, the United States had not only achieved unprecedented scientific and technological dominance in wartime, but had also fundamentally altered the landscape of global power. Atomic weapons, advanced radar, supersonic aircraft, and early guided missiles converged to create a toolkit of strategic capability that no other nation could match. The efforts of American scientists, engineers, and industrial workers had reshaped the nature of warfare, demonstrating that intellect, innovation, and coordinated effort could rival armies and navies in determining outcomes. The race to build weapons the world had never seen had concluded with decisive results. Yet it also set the stage for an era in which the power of science itself would become a defining force in human history. As 1945 drew to a close, the scientific achievements that had driven America's war effort began to resonate across both military and civilian spheres, revealing the profound consequences of what had been accomplished. The atomic program, once an abstract theoretical pursuit, had matured into a concrete reality capable of ending global conflict in a single instant. In Los Alamos, the desert laboratory where the implosion method and uranium designs had been refined, quiet reflection replaced the constant hum of experimentation. Scientists walked among the meticulous assembly lines and test chambers, fully aware of the destructive power contained within the devices they had built. The exhilaration of achievement was tempered by an acute awareness that humanity had entered uncharted moral and technological territory. At Oak Ridge and Hanford, the production complexes continued their operations, ensuring a steady supply of fissile materials even as the war's end approached. The coordination of thousands of workers across enormous facilities remained a marvel of industrial engineering and logistical precision. Uranium and plutonium, once mere elements in a laboratory notebook, had become tangible agents of power, each gram representing immense destructive potential. The compartmentalized workflow ensured that individual operators could contribute to the war effort without full awareness of the stakes, a system that preserved both security and efficiency. These sites embodied the full scope of America's ability to transform scientific theory into strategic capability, demonstrating the industrial power necessary to support revolutionary weapons. Radar and electronic warfare systems, now fully integrated into combat operations, had permanently changed the dynamics of war. Pilots, navigators, and commanders relied on real-time intelligence from electromagnetic detection and jamming systems, making operations faster, safer, and more effective. Night missions, once perilous and unpredictable, became precise, data-driven campaigns. Anti-submarine operations, coordinated with radar-equipped ships and aircraft, dramatically reduced Allied losses and secured vital supply lines. These technologies showcased how mastery of previously invisible forces, electromagnetic waves, frequencies, and pulses, could decisively alter strategic outcomes, highlighting the profound importance of scientific innovation in modern military operations. Aeronautical engineering had also achieved feats that would reverberate long after the war. Propeller-driven planes had been refined to their maximum potential, while jets and rockets hinted at a new era of speed and altitude. Engineers had solved challenges in aerodynamics, thermal stress, and structural integrity, often working at the limits of known material science. Collaborative feedback between pilots, engineers, and theoreticians created a rapid cycle of innovation that turned prototypes into operational aircraft in record time. These advances not only contributed to immediate combat effectiveness, but also laid the foundation for post-war aerospace exploration, foreshadowing supersonic travel and spaceflight decades in advance. Rocket and missile programs, still in their experimental phase, had demonstrated the promise of guided warfare. Desert and isolated test ranges had produced incremental successes in propulsion stability, aerodynamic control, and trajectory guidance. Each failure was meticulously analyzed, providing critical insights that accelerated development. Observing German V-2 attacks had underscored the urgency of this work, and American teams moved quickly to ensure that guided weapons could serve as both deterrent and operational tool. These early experiments not only reshaped strategic thinking during the war, but also seeded the technological foundation for the post-war space race and missile programs that would dominate Cold War geopolitics. The human dimension of these achievements was inescapable. Scientists, engineers, and laborers alike wrestled with the weight of what they were building. Ethical reflection, private anxiety, and awe intermingled with professional pride. Letters, journals, and post-war recollections reveal a complex emotional landscape. Participants were exhilarated by the ingenuity required to achieve their goals, yet haunted by the destructive power they had unleashed. These feelings underscored the profound responsibility inherent in large-scale scientific mobilization, a responsibility that would echo into post-war debates over the control and use of nuclear weapons, guided missiles, and other technological breakthroughs. Industrial coordination reached a level of sophistication never before seen. Factories produced precision components whose tolerances were critical to final weapon functionality. Laboratories processed data and refined designs at a national scale, and field test ranges converted theory into practical understanding. The seamless integration of disciplines, from physics and chemistry to engineering and logistics, demonstrated that complex, distributed human efforts could achieve unprecedented outcomes. This model of scientific-industrial collaboration would inform both military and civilian projects in the post-war era, including energy production, aerospace engineering, and advanced research networks, setting a new standard for large-scale innovation. By the end of 1945, the United States had not only succeeded in producing weapons the world had never seen, but had also fundamentally transformed the nature of human conflict. The convergence of nuclear, aeronautical, radar, and missile technologies created a multidimensional arsenal that reshaped strategy, ethics, and global power. Scientists, engineers, and industrial workers had collectively expanded the boundaries of what was technically possible, demonstrating that intellect, coordination, and determination could rival traditional military forces. The unprecedented achievements of this period left an indelible mark on human history, heralding a new era in which scientific innovation would define the outcome of wars and the future of civilization itself. As 1945 drew to a close, the scientific achievements that had driven America's war effort began to resonate across both military and civilian spheres, revealing the profound consequences of what had been accomplished. The atomic program, once an abstract theoretical pursuit, had matured into a concrete reality capable of ending global conflict in a single instant. In Los Alamos, the desert laboratory where the implosion method and uranium designs had been refined, quiet reflection replaced the constant hum of experimentation. Scientists walked among the meticulous assembly lines and test chambers, fully aware of the destructive power contained within the devices they had built. The exhilaration of achievement was tempered by an acute awareness that humanity had entered uncharted moral and technological territory. At Oak Ridge and Hanford, the production complexes continued their operations, ensuring a steady supply of fissile materials even as the war's end approached. The coordination of thousands of workers across enormous facilities remained a marvel of industrial engineering and logistical precision. Uranium and plutonium, once mere elements in a laboratory notebook, had become tangible agents of power, each gram representing immense destructive potential. The compartmentalized workflow ensured that individual operators could contribute to the war effort without full awareness of the stakes, a system that preserved both security and efficiency. These sites embodied the full scope of America's ability to transform scientific theory into strategic capability, demonstrating the industrial power necessary to support revolutionary weapons. Radar and electronic warfare systems, now fully integrated into combat operations, had permanently changed the dynamics of war. Pilots, navigators, and commanders relied on real-time intelligence from electromagnetic detection and jamming systems, making operations faster, safer, and more effective. Night missions, once perilous and unpredictable, became precise, data-driven campaigns. Anti-submarine operations, coordinated with radar-equipped ships and aircraft, dramatically reduced Allied losses and secured vital supply lines. These technologies showcased how mastery of previously invisible forces, electromagnetic waves, frequencies, and pulses, could decisively alter strategic outcomes, highlighting the profound importance of scientific innovation in modern military operations. Aeronautical engineering had also achieved feats that would reverberate long after the war. Propeller-driven planes had been refined to their maximum potential, while jets and rockets hinted at a new era of speed and altitude. Engineers had solved challenges in aerodynamics, thermal stress, and structural integrity, often working at the limits of known material science. Collaborative feedback between pilots, engineers, and theoreticians created a rapid cycle of innovation that turned prototypes into operational aircraft in record time. These advances not only contributed to immediate combat effectiveness, but also laid the foundation for post-war aerospace exploration, foreshadowing supersonic travel and spaceflight decades in advance. Rocket and missile programs, still in their experimental phase, had demonstrated the promise of guided warfare. Desert and isolated test ranges had produced incremental successes in propulsion stability, aerodynamic control, and trajectory guidance. Each failure was meticulously analyzed, providing critical insights that accelerated development. Observing German V-2 attacks had underscored the urgency of this work, and American teams moved quickly to ensure that guided weapons could serve as both deterrent and operational tool. These early experiments not only reshaped strategic thinking during the war, but also seeded the technological foundation for the post-war space race and missile programs that would dominate Cold War geopolitics. The human dimension of these achievements was inescapable. Scientists, engineers, and laborers alike wrestled with the weight of what they were building. Ethical reflection, private anxiety, and awe intermingled with professional pride. Letters, journals, and post-war recollections reveal a complex emotional landscape. Participants were exhilarated by the ingenuity required to achieve their goals, yet haunted by the destructive power they had unleashed. These feelings underscored the profound responsibility inherent in large-scale scientific mobilization, a responsibility that would echo into post-war debates over the control and use of nuclear weapons, guided missiles, and other technological breakthroughs. Industrial coordination reached a level of sophistication never before seen. Factories produced precision components whose tolerances were critical to final weapon functionality. Laboratories processed data and refined designs at a national scale, and field test ranges converted theory into practical understanding. The seamless integration of disciplines, from physics and chemistry to engineering and logistics, demonstrated that complex, distributed human efforts could achieve unprecedented outcomes. This model of scientific-industrial collaboration would inform both military and civilian projects in the post-war era, including energy production, aerospace engineering, and advanced research networks, setting a new standard for large-scale innovation. By the end of 1945, The United States had not only succeeded in producing weapons the world had never seen, but had also fundamentally transformed the nature of human conflict. The convergence of nuclear, aeronautical, radar, and missile technologies created a multidimensional arsenal that reshaped strategy, ethics, and global power. Scientists, engineers, and industrial workers had collectively expanded the boundaries of what was technically possible, demonstrating that intellect, coordination, and determination could rival traditional military forces. The unprecedented achievements of this period left an indelible mark on human history, heralding a new era in which scientific innovation would define the outcome of wars and the future of civilization itself.